Hi there, this is Magnetism lesson 7. It's on transformers. It's the power equation and how to increase efficiency. So transformer power transfer equation. If a transformer is 100% efficient, then the power input to the primary coil is equaled by the power output from the secondary coil. So we end up with current on the primary coil multiplied by voltage on the primary coil is equal to current on the secondary coil multiplied by voltage on the secondary coil. It's just power equals power. Obviously, you know, at A level, it's not always 100% efficient. We could have 0.75 or 80%, 90%, 0.96. Next lesson, we'll take that into account and we'll practice some of those questions. So current's measured in amps and voltage is measured in volts. So let's get straight into it. Let's pause and have a go. Calculate the primary current. If when a transformer is supplied with 230 volts, the secondary provides 4 amps at a voltage of 13 volts. So we're assuming that the transformer in this instance is 100% efficient. So we've got current on the primary coil multiplied by voltage on the primary coil equals current on the secondary coil multiplied by voltage on the secondary coil. So primary current is what we're looking for, IP. So voltage primary is 230 volts equals current on the secondary is 4 times voltage on the secondary 13. So current on the primary is simply 4 times 13 divided by 230. And that gives us a current value of 0.23 amps. Should be pretty straightforward. Let's move on to the next one. So let's pause and have a go. Calculate the secondary current from a transformer supplying a secondary voltage of 6 volts if the primary is supplied with a current of 0.2 amps at 230 volts. Again, we're assuming in this instance that the transformer is 100% efficient. So the power on the primary is equal to the power on the secondary. So we've got current primary times voltage primary equals voltage secondary current secondary. I know I said that backwards, but still the same thing. So we're calculating secondary current. So let's put the values in. So we've got 0.2 amps at the primary multiplied by 230 equals voltage on the secondary is 6 volts times current on the secondary. So 0.2 times 230 divided by 6 gives us the current on the secondary, which is 7.6 recurring. So 7.7 amps. If you've got 7.6 recurring, that's fine. Right, let's move on. So plenty of practice on this page if you want to fill this table in. So if you want to pause and have a go, and then I'll reveal the answers before we move on to more A-level type content in how to improve the efficiency of transformers. So let's look at the answers. So the first one, 10 volts. Next one, 8 amps. Next one, you should have got 4,000 turns. And then 0.2 amps. 12 volts. 0.4 amps. 25 volts. And finally, 50 turns. So hopefully that went okay. That's kind of the GCSE recap finished in essence. So next we're going to look at some purely A-level content. So transformer efficiency, there's 4 ways to increase transformer efficiency. You could get a long answer question where we have to talk about each of these in detail. So what the issue is and how we fix it. So there's going to be a lot of note taking. You've got a bit to remember. It does link in well with other aspects of physics which we've covered previously though. So let's have a look. So when a transformer is in operation, there are AC currents in the primary and in the secondary coils. The coils have electrical resistance, and this causes heating in the coils, which results in energy losses via heat to the surroundings. So obviously we need to minimize that. So the energy losses, the fix, can be reduced by minimizing resistance. We can therefore use low resistance coils. It's very important for any coils carrying a high electric current to have a low resistance. So thick copper wire is used for the coil windings, as thicker wire, as you should know, has a larger cross-sectional area and resistance is inversely proportional to that area. So that's just straightforward. Resistance is proportional to 1/A from year 12 electricity. It basically links in with this equation. The resistance is equal to rho L/A, if you remember that experiment. So if you want to get those notes down, pause and then move on to the next point. So next one, the primary alternating current magnetizes and demagnetizes and then remagnetizes the iron core at a rapid rate in opposing directions, obviously because it's an alternating current, so you set up an alternating magnetic field. Energy is required to do this, and energy is simply transferred to the surroundings as thermal energy during this process. So what we need to do is minimize the heat buildup of this magnetization demagnetization process. So we can reduce thermal energy losses in the core by making the core from a material that is easily magnetized and easily demagnetized. So what we do, we say that the material is magnetically soft. Iron is a magnetically soft material and it's typically used in a transformer. So if you hear the term soft iron, it's not because iron is soft. Iron's not soft, it's actually very dense, as you know, but it's magnetically soft, which means it's easily magnetized and easily demagnetized. So make sure you pause and get some notes on that one, and then move on to the next point. So there's 2 more left to do. It's point 3. So as we know, in a transformer, an alternating B field or magnetic field is set up inside the iron core of the transformer. The continuous change of flux induces EMFs in the core itself. So in a continuous solid core, these induced EMFs will produce currents, and these currents are known as eddy currents. Eddy currents heat the core and cause thermal energy to be lost to the surroundings. So the way that we get around this is transformer cores, in case you ever wondered why they're laminated, as you're told at GCSE, they're laminated in layers rather than a continuous solid block, and the laminations are separated by thin layers of insulating materials. And we do this because currents cannot flow in discontinuous materials such as this. Therefore, the eddy currents can never establish themselves, or the EMFs can't really, well, the EMFs can set up, but there's no current flow, so there's no eddy currents. Therefore, we don't lose energy from the transformer via heat. So laminating the cores is very important, and make sure in an exam, if it asks you about this, you need to say that there's an insulating material in between each layer. And remember, lamination is just layers of iron on top of each other, just like laminated wooden flooring. Obviously they're next to each other, but it's the sheets. So laminations are like sheets of iron. Let's move on to the last point. If you need to make notes, just pause. So last point. For a transformer to be efficient, as much of the magnetic flux produced in the primary coil must cut the secondary coil as is possible. So remember, the flux cut in the secondary coil results in electromagnetic induction. Ignore my typo. So to do this, it's quite straightforward. To ensure this happens, the distance between the primary and secondary coil is kept as close as possible. Well, that's it. So when it's magnetized, see if I can draw a little image. So we've got both coils. So you've got your primary coil and your secondary coil. When when an alternating current is put through the primary coil, remember your magnetic field is set up like this, and it cuts through the secondary coil. If I shorten this distance, up, then more of my alternating magnetic field would cross the secondary coil, and it would increase the rate of electromagnetic induction. So I hope that's okay. Remember, how to increase the efficiency of a transformer could be a 6-mark question. There's 4 points that you need to know. So the problem, and then the fix, like the solution to it. So there's 4 in total. Make sure you know them all. Write them down, make some notes. And I hope you enjoyed that, or at least found it useful. Thanks for watching, and I'll speak to you soon. I'll see you at the next one.